Okay, so here we go with some um, instantaneous voltage, frequency, RMS, and things of the kind. They're all interrelated in some way. So I guess frequency. So what we have here, Unit 16 is what some of these lessons are. I think these lessons are based on all parts. So Unit 16, check that out. So here we have a sine wave. And we'll just say this is positive and negative. Now again, positive and negative isn't really plus and minus. It's just a matter of direction of flow. So in the positive, we'll just say that they're flowing this way and negative is flowing this way. So we have, and again, when we're dealing with a circle, or when we're dealing with a sine wave, we're dealing with a circle that is set to time. So here we have 90 degrees, 180 degrees, 270, 360. This axis here is your time axis. So as time is traveling, the voltage is increasing and it's decreasing. And that here we have 0 volts. And that here we have 0 volts. So anyway, just to get into a little bit of terminology here. So at this point we have your Emax. This is our maximum voltage. And for these exercises coming up, it really comes back to Emax all the time to find our other values. So we have plus, positive, we have negative, 1 volt, the magnitudes being equal in strength. So we have a little bit of terminology here. So we have the peak, so this is your peak positive, this is your peak negative, and then between we have our peak to peak. So if we have 1 volt positive, 1 volt negative, peak to peak, we have 2 volts. So our RMS, now RMS stands for root mean square. And I'll elaborate on that in a bit, but just for the sake of the math of it here. So the RMS, the root mean square, is the value that occurs the most. So when you have a meter and you take a reading, and you get 120 volts. What you're going to read is the RMS value, not the peak value. So in our meters, 120 volts is the RMS. So that is equal to the peak times 0.707. So the RMS, so when we want to find out our RMS value, so we can say peak, we can say max interchangeably. But we'll take our Emax times 0.707. So say our Emax equals 170 volts. So we take 170 volts times 0.707 gives us roughly 120 volts. So if we want to just go in reverse, we have our Emax is equal to the RMS times 1.414 or divided by 0.707. Recognize this number. So the RMS would be equal to 140 volts divided by 0.707, and again, carrier, so this would be the square root of 2. This is 1/2 the square root of 2. So if you punch that in as such, so you take the square root of, so 120 volts divided by half of the square root of 2, you're going to get roughly 169.9 or whatever that ends up to be. So we have our RMS, but we also can track down our instantaneous voltages using our sine wave. So all we need to do is factor in the sine of the angle. So our E instantaneous, so our instantaneous voltage, what is this voltage right here? So as time is going by, what is our voltage right here? So our E instantaneous, again, it all comes back down to the Emax for these equations as we're coming and going through them. We'll say we have 170 volts max, which means we would have 120 volts RMS. So we got E instantaneous equals Emax times the sine of the angle. In this case, we have an angle of 30 degrees, which gives us 85 volts. So notice again, as we're going through these relationships, we have the formulas that we E instantaneous equals E max times the sine of the angle. We do the multiplying, the dividing, the canceling, and all that kind of stuff. But if you really think about the relationships, the formulas will just disappear because you'll understand what to do and what is happening within this wave here. So multiply by a decimal, and sine of 30, right? Sine and cos will always provide a decimal aside from 0 and 90 degrees. So it stands to reason, multiply by the decimal, your number's going down. So E max. So if I want to find E max, again, think about the relationships. Divide by a decimal and how to make a decimal, right? So for the sine of angle theta, you have to make a decimal. You're going to need your instantaneous voltage, you're going to need your maximum voltage, and you're going to have to make a decimal out of here. So you'd have to ask yourself, how am I going to stack these numbers to create a decimal? There's only one way to do that. So that's what you want to be looking for. This is the perfect kind of exercise for getting into that kind of thinking. So here, I'll give you an example. Try to pause it here after this. So think about the relationships. If. So E instantaneous. So find E max. If E instantaneous is 75 volts and the sine of the angle is 30 degrees, find the E max. You think about the relationships, don't think about the formulas. Sine of angle theta, if E instantaneous equals 35 volts, if E max equals 170 volts. So pause the video, see if you can figure it out. And here we go. So just one thing to mention here, the average voltage, it's important to understand here, an RMS it's an RMS value. We don't use the language average for this circuit because the average voltage in an AC circuit is 0 because of how it peaks and drops. Now RMS, if you want to take a note here, RMS, and you can check this out. If you add up all the instantaneous voltages and divide them by the number of measurements you took, you will get to your RMS value. That is another way of calculating. And the more measurements you take of your instantaneous voltage relative to Emax, you can set Emax at whatever you like. If it's 200 volts, well, your RMS value is going to change. So the more measurements you take of your instantaneous values, the more accurate you're going to be. Now, it stands to reason that at 90 degrees, 30 degrees, your instantaneous voltages are going to change right up to 90 degrees where you're going to hit 70. And then after that, the next line of 90 degrees are going to be exactly the same as the first half. So that's something to take into consideration there. Little food for thought. So, E instantaneous, Emax, we ended up with 85 volts. Emax, so your E instantaneous was 75, sine angle 30. So we're trying to find the Emax. You know sine is going to give you a decimal. There's only one way to do this. Sine of the angle, the ratio of the sine angle, or the voltage to the sine angle, otherwise known as 75 volts divided by the sine of 30 degrees. And when you add this into your calculator, or when you punch the numbers into your calculator, you're going to get the most accurate measurement if you go 75 divided by, and then literally punch in sine of 30. I mean, this is only going to be 0.5 anyway, but some degrees are going to give you many decimals. So instead of just going, okay, sine of 45 degrees is 0.707. You might want to elaborate on that a little more and carry all the decimals through by inputting it into your calculator in that manner. So we ended up with 150 volts was Emax, and so the sine of the angle, so we had 35 volts was our instantaneous, we had 170 was our max. There's only one way to get a decimal. 35 to 170, 0.205, yada yada. Second function, sine equals 11.8 degrees. And right here, so what that's saying is, if we have a peak of 170 at the point of 35 volts, what angle was that? Well, to achieve 35 volts, the angle was sitting around, somewhere around here, 11 degrees. You're looking at that kind of voltage. So when we get into frequency, frequency is, when we deal with our formula here, frequency is 1 over time. Also known as Hertz, expressed as Hz, F frequency, T time in seconds. So the question, this is a very simple one. What is the frequency of a waveform that takes 0.5 seconds to complete one cycle? So we just for simple numbers here, just deal with the formula as is. Frequency is 1 over time, 0.5 seconds, gives you 2 hertz. So that's 2 cycles per second. For example, we have 60 hertz here. North America, 60 hertz, 50 hertz. So that's 60 cycles per second. And if you slow that down, your lights in your house, they are flickering. They are because you have 0 volts right there. So if you slow down your frequency to 1 cycle per second, you'll literally see this get brighter and then dimmer and then off, and brighter and dimmer and then off. And you'll see that pattern. And as soon as you speed up that frequency, all of a sudden the light to our eyes is going to look like it's on constantly. But just understand that they are going on and off at some point within the cycle. So how much time does, so we're just going to invert the formula here. How much time does it take for 1 cycle if the frequency is 200 hertz? So we just do a little bit of messing around here. The time equals 1 over frequency, 1 over 200. Again, that's hertz. So hertz and 0.005 seconds, which equals 5 milliseconds. And that's a pretty simple one. So I'm just going to leave it right there. And that's the end of that video.